Welcome back for Unit 2, Lesson 2, the definition of the derivative. And in this lesson, we're going to expand on this derivative concept that we referred to in the last lesson and talk about why this is going to be important to our study of calculus. But first, what I want you to recall is what we talked about in the last lesson, which was average rate of change. And for us, that meant the slope of a secant line. So, given some function, we could talk about the average rate of change between any 2 points by connecting them with a nice straight line that intersects my function twice. And to calculate this average rate of change on some interval x, where x is some starting value, to x plus h, where h is just the interval width, was f of x plus h minus f of x all over h, or f of b minus f of a over b minus a. And what we got to talking about right at the end of that last lesson was the idea of taking this average rate of change, where I'm ignoring everything that goes on in between these 2 points and talking about the overall change, to being able to focus on instantaneous rate of change, or the change at just 1 point, say this point right here, which is going to be the slope of a tangent line. And what we used to come up with that was a limit. And the limit we used to give an expression to calculate that instantaneous rate of change or slope of the tangent line for any x value on a function, how we're going to refer to that is f prime of x. That is a prime right there. And what we said we were going to do was take our secant line, our average rate of change, and let that distance between my 2 points get very close to 0. So what we end up with is f prime of x equals the limit as h goes to 0 of the slope of my secant line. Now what I want to do is give you a visual of what I mean when I say let h go to 0, let that interval go to 0. Now notice in this visual, h has been replaced with delta x, change in x, but that's notation that we've already utilized, so it's notation that we should be comfortable with. But notice, I'm starting with a secant line on this function. And I'm sliding, physically sliding, my second point for that secant line closer and closer to this point on the left that isn't moving. And what ends up happening is as I close that distance and make it smaller and smaller, closer and closer to 0, notice what I end up with eventually, those 2 points are so close that it looks like I have a tangent line. Now the bigger question might be, why does this matter? How is this going to help us with anything? Well, I'll give you a couple examples. Let's say for some store, this is the amount of money that they have every hour. And let's say the graph of that money goes something like this. But one thing a store owner might be concerned with is thinking about how much money a store brings in per hour. If you notice in the middle, they might be concerned with this point where it seems that the rate of change, the slope, is the greatest. This is a spot where they might be making their most money. They might need to know, well, do I need more staff at that time? Is there something I can do at these other times to help myself make more money, maybe by lowering the amount of staff that's on at these times because it doesn't seem that the money is changing that much at all? Another example, and this is going to be something that's going to stick with us for most of the year, and it's the idea of objects in motion. So say we have an object thrown in the air. Could be a person going through the air, could be any sort of projectile you can imagine, baseball, soccer ball, whatever you want. Now let's let this axis be height and this be seconds. Well, if I only focused on these 2 points here, my average rate of change equals 0. But what if I were concerned with how fast this object is moving at its point of impact? That is a scenario that if I can model this situation using a function, then this concept of the derivative would allow me to describe exactly what is happening to this object at the time when it touches the ground. It would also allow me to talk about this point up here, where the object goes from increasing in height to decreasing in height, the moment where it doesn't seem like this object's height is changing at all. And so these two scenarios are just a teaser, something to give you an idea of how we're going to utilize derivatives moving forward. What we're going to do now is get back to the mathematics behind it. And the first thing I want to clear up is notation moving forward. What you just saw was called Lagrange notation, that f prime notation. The other notation that we're going to see utilized quite a bit is called Leibniz notation. And for that, you will see the derivative referred to as dy over dx. And that one actually is a very descriptive notation because that looks a lot like delta y over delta x. Change in y over change in x, rise over run. That actually looks very descriptive of slope, which is the big thing, is you need to connect that derivative is always talking about slope. So now what we're going to do is utilize that definition of derivative to find derivatives for functions. Find these expressions that can describe the slope of these tangent lines. So let's start with f of x equals 2x squared minus 7x plus 1. What we are going to set up is this limit. And recall, it is f of x plus h, so we're going to take our function and plug in x plus h everywhere we see an x, minus f of x, which is the function just the way it's written, all over h. Now evaluating that limit, now we've got to think back a little bit of review from our previous unit. I can't evaluate that limit by direct substitution because I'd be dividing by 0. That'd be 0 over 0. That would be my indeterminate form. That's no good. So we have to manipulate this. First thing I see I can do is I can expand the numerator. X plus h quantity squared times 2, that can be 2x squared plus 4xh plus 2h squared. Distribute that negative 7 and a plus 1. Don't forget to distribute my minus sign here. Minus 2x squared plus 7x minus 1 all over h. Now that's quite a bit to get down, but all algebraic steps that we should be able to take. Let's see what that allows us to do. If I look in my expression now, well, I have a 2x squared minus a 2x squared. I can get rid of those. I have a negative 7x plus 7x. I have a 1 minus a 1. And what I'm going to be left with is the limit as h goes to 0 of 4xh plus 2h squared minus 7h all over h. I can now factor out an h from that numerator. And that means that that h is actually a removable factor, so that 0 is a removable discontinuity, and what I'm actually dealing with is the limit as h goes to 0 of 4x plus 2h minus 7. And direct substitution would tell me that I'm dealing with 4x plus 2 times 0 minus 7, and my derivative, f prime of x, equals 4x minus 7. And what that represents is the slope of any tangent line, the instantaneous rate of change for any x value along my f of x function. So to give you an idea of what that might look like, I've already taken the graph off of my calculator for 2x squared minus 7x plus 1, our derivative, f prime of x, 4x minus 7, and let's just say, for example, we did f prime of 2, so the tangent slope at x equals 2. Well, f prime of 2 would equal 4 times 2 minus 7 equals 1. I would say that I have a slope of 1 at x equals 2. If I go to x equals 2 and use these dots to approximate a line with a slope of 1, it definitely seems reasonable that this could be the tangent line at that point, and that is what this function is helping us describe. Let's look at example 2. Y equals 1 over x. So what we were trying to find here, and notice I'm going to change up the notation because in this one I started with f of x, so I went to f prime. In this one I'm starting with y, so I'm describing the change in y versus the change in x. And that's going to equal the limit as h goes to 0 of f of x plus h, so replacing my x with an x plus h, minus f of x all over h. And again, if I were to try evaluating this directly, I'm going to get the indeterminate form. Can't do that. So we've got to see if there's some way we can manipulate that in order to get rid of the h. And what I see right away is two fractions in the numerator. I would prefer to have those as one with a common denominator. And I can get a common denominator by multiplying this numerator and denominator by x, and over here, x plus h over x plus h. And I will get the limit as h goes to 0 of x over x times x plus h minus x plus h all over h. And now let's start simplifying some things. So the limit as h goes to 0, well, x minus x plus h, those x's are going to cancel out. Just be careful here, so I'm doing a minus that positive h, so I'm going to have minus h all over x times x plus h, and this is going to be divided by h. To make it a little easier to read, what I'm going to do is move that divided by h and make it a 1 over h times that fraction from the numerator, negative h over x times x plus h. And notice that when we do that, we can cancel this h from the denominator and this h from the numerator. And what we'll be left with is the limit as h goes to 0 of 1 times that negative sign is going to be negative 1 over x times x plus h. And now I can evaluate this at 0. What I'm going to get, dy dx, equals negative 1 over x times x plus 0, or x squared. And there is my final derivative. Now this example at the bottom of the page is giving you another chance to break down exactly what the derivative is describing. So reading this problem, if f represents how many meters you have run and x represents the minutes, describe in full sentences the following. F of 8 equals 1,500. Well, knowing our function notation, we know that 8 is a value for x, and this 1,500 is a value for f. So what this would mean for us is that after 8 minutes, you have run 1,500 meters. Now let's look to the one on the right. F prime of 3 equals 161. Well, that 3 is still a value for x, but f prime is going to describe df dx, the change in f over the change in x. And so what we're saying is at 3 minutes, you are running 161 meters per minute. And I didn't get those units by mistake. It's a change in f was meters, over a change in x, and x was minutes. And so this example just serves to emphasize the difference between an f of x function and its derivative, but also what the derivative is actually describing, which is maybe more important than anything else that we do here, is getting a firm understanding of what these values are going to represent. So what we're going to finish with is an alternate definition for the derivative, and then end with a few more examples just to kind of drive the point home. What our second definition is going to be is for finding the derivative at a specific x value. And so the first way we can do that is just to realize that all I'm changing from my original definition is I don't want to worry about some random x value to start with. I'm going to use this constant c value. Notice the x's have just become a defined number. The other option is to think more like the average rate of change and take a limit as x goes to that c value for f of x minus f of c all over x minus c, saying that I have one defined point that I'm working with, and I'm letting it get closer and closer to any other point. And the only reason we're going to even think about using this definition is in case we only want to find a derivative at a single value, and we don't want to go through the trouble of getting our derivative function. So look to example 4. Find f prime of negative 2 if f of x equals 2x squared plus 1. What we're trying to find is a derivative at a particular value. Let's go with this definition right here. So what we're going to do is define f prime of negative 2 as the limit as x goes to negative 2 of f of x, which was 2x squared plus 1, minus that function evaluated at negative 2, all over x minus the negative 2, or x plus 2. Now to evaluate this limit, what we're going to do is we're going to expand out the numerator, and so we'll get 2x squared plus 1 minus, this will be 2 times negative 2 squared, so that'll be 8 plus 1 minus 9, all over x plus 2. Simplify that another step here, and we'll get 2x squared minus 8, all over x plus 2. And that is something I can factor. That will factor into 2 times x plus 2 times x minus 2, all over x plus 2. And we can now see that this is a removable discontinuity, and we'll be left with the limit as x goes to negative 2 of 2 times x minus 2, or, evaluating that by direct substitution, negative 8. So you can see, instead of having to go through getting the function and then substituting the negative 2, it allows you to cut out some of the middle work. Let's look at example 5 now. F of x equals x cubed minus 3 over x, and I'm giving you the derivative. F prime of x equals 3x squared plus 3 over x squared. Find the equation of the tangent line at x equals 2. Well, for our tangent line, what we're going to need, just like any line, we're trying to get to y equals mx plus b. So we're going to need at least two things. We're going to need a point for my tangent line. Well, I have an x value for that point, x equals 2, but I don't have the y value. Well, I get that from my original function. So 2 cubed minus 3 over 2, and f of 2 is equal to 13 over 2. Now the other thing I'm going to need is I'm going to need my slope. And the slope I'm going to get from the derivative, from f prime of 2. And so that will equal 3 times 2 squared plus 3 over 2 squared, which will equal 51 over 4. Putting this all together, and here you can just go ahead and use point slope form. We'll get y minus our y value, 13 over 2, equals our slope, 51 over 4, times x minus the x value from the start of our problem. You can leave it like that in point slope form, but if you want to get to slope intercept, all we'd have to do is distribute and then move that 13 over 2 to the other side. And so we get 51 over 4x minus 38 over 2, or minus 19. And to finish up, I want to make sure you're able to work backwards. Given a limit definition for a derivative, can you identify the original function and where we're trying to evaluate the derivative? So for instance, I see limit as h goes to 0 of 3 natural log of 2 plus h minus 3 natural log of 2 all over h. Well, notice that 2 plus h, that reminds me a lot of my x plus h, except the x now equals a 2. That tells me I have to be evaluating f prime of 2. And the original function, changing my 2's back into x's, I can see, usually just focusing on the second part, because that's where our f of x should be. F of x equals 3 natural log of x. And the final example, the limit as x goes to 7 of 1 over square root of x squared minus 2x minus 1 over square root of 35 all over x minus 7. Well, that's got to make us think that I'm using my alternate form, f of x minus f of c all over x minus c. So it's very easy to spot the original function in this problem. It's 1 over square root of x squared minus 2x. And it's even easier to spot the c value because it's not only part of the limit, it's right there in the denominator. We are looking for f prime of 7. So that ends this section, and I again want to stress that the concept of the derivative is more important than anything else in this entire section and in this entire unit. Some of the math involved might get a little bit complicated, might get a little bit tough to work through, but if you understand the concept that derivative is the instant rate of change and is the slope of a tangent line, then you've got what you need out of this section, and then it's just figuring out what exactly are we going to be doing to evaluate and work with this concept of derivative. So please make sure that you review and summarize your notes, come up with any questions that you feel that you need to ask to better your understanding, and thank you for watching this lesson on the definition of the derivative.